Okay. What I want to do today is tell you about yet another Hopf algebra that I like very much, that I wasn't necessarily planning on discussing in the class, but again, given what I saw you choose for the projects, it seems like this is the kind of stuff that you might like too. And so I'm going to spend the class talking about generalized permutahedra and the Hopf algebra that a Hopf algebra related to them. Okay, and the point is that this. So I mean, I'll explain that generalized permutahedra are a certain kind of polytope, and this forms a very nice Hopf algebra that includes several of the Hopf algebras that we like as sub-Hopf algebras. So, for example, the Hopf algebra of matroids live in there. Both the Hopf algebras of graphs that we have discussed live in there. The Hopf algebra of posets that we discussed lives in here. A lot of different Hopf algebras live inside of this one. And the point is that, in some sense, this is the right level of generality to write down a formula for the antipode. So I'm going to show you that in this Hopf algebra there's a very nice antipode that we can then use to deduce the antipodes of all these smaller Hopf algebras. And maybe I'll just quickly mention this isn't really written anywhere, unfortunately. So this is joint work of myself and Marcelo Aguiar, an Uruguayan mathematician at Texas A&M. And we proved these things a couple of years ago, but we haven't managed to finish the paper yet. So I was hoping to finish it before the semester so I could show it to you guys, but well, we'll see. Hopefully it'll be finished soon. But if you're interested in reading more about this, we do have a kind of a draft of the paper that I can share with you. Or there's also some slides on my website of a talk that I gave about this, if you're interested in learning more. Before we try to generalize permutahedra, let's talk about what the permutahedron is. Okay? That would be a good start. So the permutahedron. And by the way, one thing about this is that it's about polytopes. And I know that some of you know polytopes very well. Some of you don't know them so well. And I could spend a whole semester talking about polytopes. And again, I have. And if you're interested, I have a course on polytopes online. But I'm just going to kind of give you some idea of some of the main ideas, and then the details. I'm happy to talk to you later about how the details work out. Okay. So the permutahedron is a polytope. It lives in Rn. And it has to do with permutations. So the permutahedron is the convex hull of the n factorial permutations of 1 up to n. Okay, so you take every single permutation sigma of the numbers from 1 up to n, and you write it as a vector, and you take the convex hull of those different vectors. Okay, and convex hull just means the polytope. Is the polytope whose vertices are the n factorial permutations. Okay? So I think this will be clearer if I draw an example. Let's say that I do pi 3. Okay? And so there's going to be 6 vertices here corresponding to the 6 permutations of 1 up to 3. And this polytope lives in 3 dimensions. So let me draw 3 axes here. Okay? And then, if you draw what this looks like and you do it carefully, you will see that it looks like this. And the coordinates look like this. And I'm ignoring the parentheses just so that this takes up a little bit less space and time. But those are the 6 vertices of this polytope. One thing that you'll realize is that even though this polytope is in 3 dimensions, it's actually a 2-dimensional polytope. And you can see that pretty quickly because you will see that even though these points are in R3, they all satisfy the same linear equation. Can you tell me what equation that is? X plus y plus z equals 6. Right? Every single one of these points satisfies the equation x plus y plus z equals 6. And we know that x plus y plus z equals 6 is a plane in 3 space. And so these points lie on that plane. And they turn out to form a regular hexagon, like you see in this picture. Okay. So this is the permutahedron pi 3. Okay. The next one, pi 4, I could draw, but I decided that instead of trying to do that in front of you and mess it up, I was just going to show you a nice picture of one. And so here it is. We'll wait for the camera to get here. Hopefully the camera can see this angle. So this is the permutahedron pi 4. Okay, and again, so this is the convex hull of 24 points, the 24 permutations of the numbers from 1 up to 4. Okay, now this polytope lives in 4 dimensions, right? But you're seeing that it's a 3-dimensional polytope, and the reason is the same as over there, that these 24 points satisfy a linear equation. The linear equation is x1 plus x2 plus x3 plus x4 equals 1 plus 2 plus 3 plus 4, which is 10. Okay, and so you can see that it looks like this. Okay. I think the camera is going to be giving me trouble today, so. Okay, so I should say that I put a picture of this on the notes, so you can see it there. And I think that the video is not showing it right now, so I'll ask everybody who's watching to look at the notes. Okay. So this is the description of the vertices of the permutahedron. Okay, but as you might know, a polytope can be described in at least in 2 ways. One way is by saying what the vertices are, and the other way is by saying what the inequalities are. Okay? So each one of these things says, you need to be below this, and so on, and you can give linear inequalities that describe this polytope. Okay? And so the inequality description of this polytope is as follows. So first we have one equation, which I already explained. So all the points of the permutahedron satisfy this equation, not only the vertices, but every point in the convex hull. And you satisfy the following inequalities. For any subset of the variables, if you sum, I don't know, let's say, for example, that you sum x plus z. How big can x plus z be? Well, if you want x plus z to be as large as possible, then you want to assign the largest coordinates to x and to z, 2 and 3. Okay? And if you have a certain number of coordinates, then the largest that could be is n plus n minus 1 plus n minus 2 up to n minus the number of elements in A plus 1. Okay? And it is a theorem that a point is in the permutahedron if and only if it satisfies these inequalities. This equality and this inequality should be satisfied for all subsets A of n. Okay? And I actually encourage you to look at these 6 edges and see how each one corresponds to one of these inequalities. Okay, so that is the permutahedron. Now, let me say what a generalized permutahedron is. So a generalized permutahedron is a deformation of these guys. Is obtained from the permutahedron by kind of pushing and pulling the facets. By facets, I mean the faces of dimension d minus 1, where d is the dimension of the polytope. So in other words, you kind of push the inequalities or pull them a little bit. So by moving the facets, let me say like that, pushing and pulling the facets. The facets without having them cross vertices. So let me explain what I mean by this. So for example, let's say that I take the permutahedron pi 3. Okay, there it is. And now I'm gonna allow myself to push some of the facets. Okay, and now here a facet is just one of the edges, and so I can say, for example, that I'm going to push this facet a little bit, and then maybe I'll pull this one in a little bit. Okay, and so then I'm gonna get something that looks like this. Maybe I'm pulling this one in like this, and so I get something like this. Okay. So I kind of push this a little bit, and then maybe I push this one in a little bit also. You're just kind of moving the things in parallel, and you can even keep pushing. I can keep pushing this edge up so that I can push it so far that actually it disappears. Okay, and then these two meet. Okay, and this is okay. Now let me show you what is not okay. What is not okay, so this is good, but what is not okay is the following. Let's say that I take two. So look at two of the squares in the three-dimensional permutahedron. Okay, so let me kind of draw some schematic thing here. Yeah.
Which edge did you push on the vertical?
I pushed this edge up,
Okay.
and it's shrinking and it's shrinking and then it ends up disappearing.
Okay.
Yeah. So it ends up being a pentagon instead of a hexagon. And that's okay. Let me show you what is not okay. So here's part of the three-dimensional permutahedron. Okay, you can see that you have these two squares, and then there's two hexagons here. Okay, and I can imagine pushing the two squares in a little bit. And you see if you push the squares into the polytope, they become bigger. So you can push them, and then they become bigger, and the distance between them becomes shorter. Okay, and so far that's okay. But what I'm saying is that you should not cross vertices as you push. Okay, and so what I mean is that I shouldn't push this face so much that it crosses this vertex. You see, if I did, then these things would collide, and what would happen is that it would end up looking something like this. So they got even bigger. And now these two faces collided, and they actually collide like this. Right? Can you see that? These two faces collide and form a new ridge between them that was not in the original polytope. And this is what is not okay. And that's what I mean by not crossing vertices. Okay? So maybe I should say that this step is okay, and this step is okay. And here, this step is okay, but this is not okay. Okay, so this thing should not be considered a generalized permutahedron. Okay? So this is a geometric description of what it means to be a generalized permutahedron. Question?
However, if you, so the most you could push those two diamonds is so that they are touching each other at that vertex. That'll be the most you could do.
That's right. So you could push them to touch each other at the corner and make these edges appear, and that's okay. You just cannot push past that and create new ridges that didn't exist in the original polytope. Okay? So this is some kind of geometric description of what it means to be a generalized permutahedron, but the issue with this is that already in 3 dimensions it's a little bit hard to visualize this. I mean, it's okay, you can see it. But we're going to move to higher dimensions, and it's going to be harder to understand what this looks like in higher dimensions. Okay? And so let me make a proposition / definition that the generalized permutahedra, and I'm going to keep writing gen perm for generalized permutahedra, are precisely the polytopes of the form let's think about this. We started with the original permutahedron, right? And we gave 2 different descriptions of it. We gave a vertex description, and we gave an inequality description. Now, we're pushing and pulling the facets, and the facets are the inequalities that define the polytope. And so it's going to be more useful to think of this description in order to describe what's going on there. Okay? Now think about it. If you take a facet and it's in a fixed direction, and you push it, like, I don't know, maybe, for example, this inequality right here is saying what? It's saying z, let's see, x plus z is bigger than, y is bigger than or equal. I think I labeled the edges, the axes wrong. Because here, yeah, sorry, this is y. And I don't know what these are anymore. But the reason that I know this is y, no, I think I labeled this all wrong. I'm sorry. Just forget what the axes are. And let's look at this inequality. Here we have that y is equal to 1. Okay? I think I totally messed up the axes. Okay? They're somewhere else. Because you see, here y is equal to 1, here y is equal to 2, and here y is equal to 3. Right? And so really the y-axis should be pointing in this direction, which is not how I drew it. Okay? These things are hard to draw. But anyway, you see the y-axis goes in this direction, and so this is the inequality saying y is greater than or equal to 1. If I push it, it's going to say y is greater than or equal to 1.5, let's say. If I pull it, y is greater than or equal to 0.5. But my point is that the left-hand side of the inequality stays the same and the right-hand side changes, according to how much you push or pull. And so we know that any polytope that we can obtain in this form has to be it has to look like this. This has to be the left-hand side. And let me, just to be a little bit more consistent with the notation, I'm going to call this set n E. Okay, so E is just going to be the set from 1 up to n. And we have some numbers here. Okay, and the numbers just, each number just depends on how far you pushed or pulled that particular facet. So in principle, these numbers are kind of independent. I'm just going to give them names. So I'm going to call them z of whatever the variable is, z of whatever the set is. Okay, so these are the parameters that tell you how much you pushed or you pulled. Okay, and so I'm saying that these are kind of independent from each other, but that's not exactly true. And the reason is that I need to make sure that I don't pull too much or I don't push too much, that I make facets clash when they shouldn't clash. Okay, and so there should be some condition on these z's, and that's what I'm going to describe to you. So what can I put on the right-hand side? Z. So z is going to be a function that to each subset. I mean, this is for all subsets of E, and here E we said is the set of numbers from 1 up to n. Okay? So z is some function that assigns to each subset some number, some real number. And I need to make sure that those numbers didn't push or pull too much. And it turns out that the condition is that this should be what's called a submodular function. And that means that z of A plus z of B should always be greater than or equal to z of the union plus z of the intersection. Okay? This is very much a non-trivial statement. I'm claiming that these are precisely the inequalities that tell you you didn't push too much or pull too much. Okay? And that's why I say it's a proposition, but sometimes people just write this as the definition. And so that's why I say it's a proposition slash definition. Okay. And so this can be our working definition for what a generalized permutahedron is. It's a polytope given by inequalities like this, where the parameters on the right-hand side satisfy this. Okay. Any questions about this so far? Yep. Oh, I see what you're saying. Here, this should also be like this. Okay. So let's do some examples. Because again, as with anything, you could define, you can make definitions, but the point is, are there examples of this that are interesting, and can I prove theorems about this? Because if this is worth studying, there should be interesting examples, and I should be able to prove theorems about this. And so I'm going to, first of all, the answer is that, yes, there's many, many, many examples, and there's whole books written about, for example, I'm pretty sure that if you go to the library and look up submodular functions, then there should be a book either called that or essentially treating that. Okay. There's lots of submodular functions around, and I'm going to show you 3 examples. And these 3 examples are going to come from 3 different places. So my first example is going to be graphs. Okay? So let's say that I have a graph G. Let's say that the edges are E. So the vertices are labeled by V, and the edges are labeled by E. And let's say that this graph is not directed. And so the edges don't have directions. They're two-way edges. And it might be that you have loops or repeated edges. That's fine. Let me define a function. The function is going to be a function from the subsets of the vertices to the reals. And it's going to be given by this. So for every subset of the vertices, I'm going to say that the number I associate to it is the number of edges incident to a vertex in W. Okay? And so I think we would be well served if we do an example such as this one. Okay? Let's say that these are my vertices. Okay? And now I'm going to define ZG of for every subset of the vertices, I have to say what Z is. Okay? As often is the case, Z of empty is easiest and most confusing. So let's do something that is maybe a little bit clearer. So what is Z of 1? Now, really, I should be, Z is defined in a subset, okay? And so 1 should be in curly braces. What is Z of the set 1? It's the number of edges incident to a vertex in that set. So the number of edges incident to vertex 1. And so here's vertex 1. There's 3 edges incident to it. Okay? And let me just drop these things because it's going to look a little bit nicer. So this is 3. Right? But I'm leaving space because also by symmetry, Z of 2 is also 3, right? Because 1 and 2 look the same in this graph. And actually, Z of 3 is also 3, right? There's 3 edges incident to the vertex 3. Okay? Z of 4 is not 3, because there's only 1 edge incident to vertex 4, so Z of 4 is 1. Okay? Then maybe, I don't know, what is Z of 1, 2? Number of edges which are incident to either 1 or to 2. So how many are there? 4, right? There's these 4, but this one is not incident to 1 or 2. So Z of 1, 2 is 4. Z of 1, 3, for example. What is Z of 1, 3? Well, actually, you see that everything in this picture is incident to either 1 or 3. So Z of 1, 3 is 5, and etc. Okay? You do this for all the Z's. Okay? And so here's a nice claim / proposition / exercise, or whatever you want to call it. Proposition. This is a submodular function. So what does this mean? It means that no matter what pair of sets you choose here, like let's say you choose 1, 2, and 1, 3. Z of A plus Z of B should be less than or equal to Z of the intersection plus Z of the union. Greater than, thank you. Probably not the only time I'm going to confuse that, because actually there's the two conflicting notations. Sometimes it's more customary to talk about submodular, but you can also talk about supermodular, where you reverse the inequality and the theory looks exactly the same. So is this true? Z of 1, 2 is 4. Z of 1, 3 is 5. So this is 9. Z of 1 is 3. And Z of 1, 2, 3 is... Well, everybody's incident to either 1, 2, or 3. So Z of 1, 2, 3 is 5. And so I get 9 greater than or equal to 8. And so this inequality is true for this particular set, but what I claim is that it's true for any two sets that I could have chosen here. Okay? So this is submodular, and therefore it defines a polytope. Okay? And I should have given a name. So I'm going to call this polytope P sub E of... Or maybe I'll just call it P of Z. Let me see. Where did I call it in my notes? I guess I called it GP of Z for generalized permutahedron of Z, of the form like this. Okay? And so the point is that because this is submodular, it defines a polytope. And so the generalized permutahedron that I obtain, this is called the graphic zonotope. Of G, okay? Or graphical, maybe graphical is more common. The name is not too important. The point is that given any graph, you get a polytope. And that polytope is a generalized permutahedron. And that polytope knows a lot about the graph. Okay. Is that okay? We'll see what I mean by saying that that polytope knows a lot about the graph. But let's do another example. But by the way, you should check that this is a submodular function. That's a nice, simple combinatorics exercise, right? It's really a nice exercise about graphs.
What's the empty set?
Oh yeah, what is the of the empty set? Brian is going like this: 0. Number of edges that are incident to. They're not required to be incident to anybody. I don't know. It's 0. 0 of empty set, maybe by convention, is 0. Incident to a vertex in there. Well, there's no vertices in there, so you can't be incident to them. That's why I said that it's the simplest, but sometimes it's the most complicated to think about. Okay. Example 2. Example 2 is matroids. Okay, so let's say that I have a matroid. Given a matroid M, the matroid polytope is well, this is traditionally there's a couple of ways of defining this, but one way of defining it is by saying what are the vertices, and that's what I'm going to do. So convex hull of the following set. I'm going to have a vertex of the polytope for each basis of the matroid. Okay, and I'm going to call that vertex B, that vertex EB, where B is a basis. Okay. Now, what is EB? Or maybe I should first say, where does this polytope live? It lives in R to the E, where E is the ground set of the matroid. Okay, so that's where the elements of the matroid come from. And this vector EB is just going to be a vector of zeros and ones. Okay. Where the ones tell you what B is, and the zeros tell you what B is not. Okay. So the ones tell you precisely what are the elements of the basis. Okay. So again, I think it's useful if we do an example. Let's pick our favorite matroid. So E is the numbers from 1 to 6. You should think A, B, C, D, E, F. And the bases are 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 3, 4, and 1, 3, 5. And this was my running example of a matroid from the last class. And for example, it was the matroid of this graph. Okay. So the bases here are what are called the spanning trees here, the sets of edges that touch all the vertices and don't contain any cycles. The trees that reach out to every single vertex. Okay. So now I'm going to make a polytope out of this, where I am going to have a vertex for each one of these guys. Okay. Where does that polytope live? It lives in R to the this. So it lives in R6. And that might scare you a little bit because I'm about to draw a polytope that lives in 6 dimensions. But, well, how bad can it be if it only has 5 vertices? That can't be too complicated of a polytope. We know what the coordinates are. For example, what is the coordinate of this vertex here? It has to be a 6-dimensional vector, which has 1s in these positions. So it has to be the vector 1, 1, 1, 0, 0, 0. Okay? And how do we draw that? Well, you know, we do this in the plane. We just pick some random point and call it 1, 1, 1, 0, 0, 0. Okay? Now we need to do 1, 1, 0, 1, 0, 0, etc. And okay, now you have to think about it a little bit more, but when you're done, you'll see that the picture looks like this. And I will try to convince you why it looks like this. So this is 1, 1, 0, 1, 0, 0. This is 1, 1, 0, 0, 1, 0. This is 1, 0, 1, 1, 0, 0. And this one is 1, 0, 1, 0, 1, 0. Okay? So I claim that even though this polytope lives in 6 dimensions, it's actually just a square pyramid. A 3-dimensional square pyramid. Okay? Now, how can I convince you of this? Well, one way of doing it is the following. Look at the difference of these 2 vertices. What is this vector? No matter what the dimension is, this vector is this minus this. So what is this minus this? 0, 0, 0 minus 1, 1, 0. What is this vector? This minus this is 0, 0, 0, 1 minus 1, 0. It's the same vector. When you do this minus this, you get the same thing as when you do this minus this. Okay? And therefore, these 2 vectors are parallel and have the same length. And so that means that at least you have a parallelogram here. Right? But you can see that actually, you can see what this vector is, and you can take the dot product of these 2 vectors, and you'll see that it's a 90-degree angle, and you'll see that they have the same length, and so it has to be a square. And then by symmetry, you'll see that this guy has to stand right in the middle. Okay? It takes a little bit of practice, but after a while, you learn not to be scared of drawing polytopes in high dimensions. This is what a lot of geometrical combinatorics is about. Okay. So one thing that you might be interested in thinking about is think about how this guy can be obtained by degenerating that guy. It's possible, and it's not so easy to visualize. But you really can push and pull facets of this 3-dimensional permutahedron to get this polytope, square pyramid. Okay. And that's a general fact that when you do this construction, you get a generalized permutahedron. Okay. So let me make a proposition that this polytope is always a generalized permutahedron. And so again, for every matroid, you obtain a polytope, which is a part of this family, and which knows a lot about the matroid. Actually, this polytope knows everything about the matroid as soon as you have the coordinates. Right? Because if I cover up this list and I show you the polytope, you can tell me what the bases are. Right? It's very easy. You say, okay, a basis is 1, 2, 3, another basis is 1, 3, 5, etc. And so this is just kind of a geometric encoding of the polytope. But the point that I want to make is that it's not just some cutesy thing to do to like, oh, let me draw a picture out of this. The point is that there's more structure now. You really have a polytope here that knows what the bases are, and it knows more. Okay? And you can really exploit the geometric structure of this polytope in order to study the matroid. Okay? Let me be even more concrete about this, because this is actually one of the one of the classic examples in combinatorial optimization. Okay, if we go back to, I mean, like I said, what are the bases here? Like 1, 2, 3 is a basis, right? And so that is this tree right here. Okay, and you can really think that this is, for example, a network of cities, and maybe these are like internet connections between two cities. I don't know. Okay, maybe cities is not. I don't really know what the right word for this is, but maybe you're trying to distribute internet from these nodes through these possible cables that you might build. Okay, and for example, if you build cable 1, 2, and 3, then all of the 4 nodes are connected. Right? If you build the connections 1, 3, and 4, then also you have connected everything. And actually, you'll see that these 5 possibilities are precisely the 5 ways of covering the whole network using building only 3 of the connections. Okay. But now you can ask, okay, so that's fine. I know all the ways of connecting this network, but I want to make money. I'm a businessman. I'm trying to get money out of people by providing them internet. And so I want to do the cheapest thing possible and still be able to charge everybody for connecting them. So let's say that building each one of these things has some cost. Okay, so maybe this costs, I don't know, let me say some random numbers, $1,000, $2,000, $1,000, and there's a cost associated to each one of these things. Okay? That is going to give me a vector of costs, the cost of 1, the cost of 2, the cost of 3, up to the cost of 6. And this is R6, remember. Even though it's 3-dimensional, this space is R6. Okay? And so if I have some vector of costs of how much it costs to build each one of these things, that precisely corresponds to a vector in R6. The cost of 1, comma, the cost of 2, comma, up to the cost of 6. Okay? And you can easily see that the cost of building this choice of connections is precisely the dot product of this vector with this vector. The dot product of this is C1 up to C6. Okay? And so the cost of building 1, 2, and 3 is C1 plus C2 plus C3, which is the dot product of this and this. Okay? And so what is the cheapest thing to do? The cheapest thing is to look for the vertex of this polytope that has the smallest dot product with this guy. Okay? Now, the dot products of this guy are actually just kind of sweeping planes up in this direction. And so what you're looking at is you're looking for the lowest vector in this direction out of the vertices of this polytope. Yeah? So in this direction, you're looking for, in this case, it seems like this might be the lowest. Okay? And so the way that you solve this optimization problem of building the cheapest network is to find the lowest point of the polytope in a certain direction. It turns out that, in the theory of polytopes, this is very easy to do, and there's algorithms, and this is precisely what's called linear programming, and this is there's theory and there's practice for how to do this. Okay? And so to solve this very concrete optimization problem, you really are led. I mean, the point of why people define this polytope is to actually solve these kinds of optimization problems. And this actually started in the optimization literature. So that's one point that I want to make, that this isn't just some gimmick. I mean, this really is something useful in matroid theory. Okay? Okay, so that's a little bit of hand-waving about why this is useful. But again, the point is, okay, from a matroid, you get a generalized permutahedron. Example 3 is going to be building from posets. So let's say that you have some poset. Okay, and I'm going to define, again, a function. It depends on the poset. a function that for every subset of the poset, it assigns a number. Now, one thing that I should have said is that actually sometimes it's useful to allow myself to put an infinity parameter here. Okay? What does that mean in terms of the polytope? You had an inequality that said, you know, x plus y plus z is less than or equal to 6. And you start pushing it less than or equal to 7, less than or equal to 8, and you just push that off to infinity. So basically what I'm saying is take that facet and just throw it out. Okay, push it away to infinity. And so there's no restriction in how far you can go in this direction. Okay? So what that's going to do is that it's going to take this polytope that was nice and enclosed, and it might make it unbounded by just pushing some of the facets to infinity. And that is allowed. Okay, that's also considered at least under the definition that I'm interested in giving, the generalized permutahedron is allowed to have facets pushed off to infinity. And I say that because I want to do that here. Okay? So what I'm going to do is that I'm going to do the following thing. For every subset of my poset, I want to do the following thing. I'm going to say that that facet gets either pulled to 0 or pushed to infinity. So you take that polytope over there, and you pull some of the faces to the origin, and you push some of them to infinity. And you do that according to whether your set is an order ideal or not. So it's 0 if you have an order ideal, and it's infinity otherwise. Okay. That's something I can do. And again, a nice proposition / exercise is that what I have defined here is submodular. Okay. And so it defines a generalized permutahedron, which I might call the Poset polyhedron of P. Okay. And it's something. It's some unbounded polyhedron. Okay. So these are 3 of the examples. From a graph, you can build one of these things. From a matroid, you can build one of these things. And from a poset, you can build one of these things. Okay. And one reason that Marcelo and I got started in this project is that we were very well aware that graphs, matroids, and posets have a structure of a Hopf algebra. And we were wondering, well, if all of these things live inside this world of polytopes, can we talk about putting a Hopf algebra structure on those polytopes? So that'll be the next goal. Goal is to make a Hopf algebra out of these polytopes. Okay. So let me show you how to do that. We need a product, we need a coproduct. Okay. How do we multiply 2 polytopes? So P is a polytope. We're going to define a product. So if P is a polytope in R to the E, and Q is a polytope in R to the F, I would like to define their product. Okay. So how do I define the product of 2 polytopes? I'm sorry? Of the vectors, you mean? There are several things that I could take products of, and I think maybe a natural thing whenever you are faced with a question like this is you look up the literature and see if polytope people have something they call a product, and hopefully it agrees with what you're trying to do. Okay. And it turns out that polytope people do have a product, and it does work. Okay? And actually, the product is exactly it's exactly the product of sets. Okay, and so it really is, the product P times Q. So what is this? These are the points P comma Q, such that P is in P and Q is in Q. Now, one thing that polytope people know is that this is a polytope, which maybe is not so obvious when I'm writing it like this. How is this even a polytope if it only has two coordinates? Well, the thing is, you have to remember that P is a vector of length E, Q is a vector of length F, and if you take a vector of length E, comma, a vector of length F, you're going to get a vector of length E plus F. And so this thing is a polytope that lives in R to the E union F. Okay? And the question is, this is a general definition of product of any polytopes, and the question is, if these guys happen to be generalized permutahedra, since I want to be close under the operations, then this one should also be a generalized permutahedron. And so then the question is, and this is kind of what Brian is suggesting, if you know the z function for this guy and the z function for this one, how do you get the z function for this one? And there's not that many things that you could try. If you try the product, you'll see that doesn't work. And if you try the sum, you'll see that it does work. Okay? And so I wrote the formula on the notes, but it's just the sum of the two functions. ENF are sets, and the only reason I say this is that if I want to call it, if this is Rn and this is Rm, and this is Rm plus n, but since I wanted to write union here, then it's a little fishy if these are the numbers from 1 up to n, these are the numbers from 1 up to m. That's why I needed this joint union. And that's why I decided to just label it with letters instead of with numbers. Okay. So product, this works, and there's nothing new to do except just study what people that study polytopes do and see that it all matches beautifully with what we need here. Okay? Now, coproduct is something that does not exist for polytopes. And so this is really where we had to think of something. And what we were thinking is that actually, again, we kind of have some motivation because we know we want this to generalize matroids, graphs, posets, and so we can basically see what worked for matroids, graphs, and posets and try to imitate it here. And for example, for matroids, we saw last time that what you're doing is you're kind of doing restriction and contraction. And so we thought, okay, maybe we can define restriction and contraction for these polytopes. And if we can, then maybe that'll be the right definition. So that's actually what we did. So we need a restriction and a contraction. And let me explain to you how that goes. So let's say that we take a polytope, a generalized permutahedron, such as this one. Okay? And now I want to define the restriction to a set and the contraction of a set. Okay? So let's say maybe this lives in Re. And let's say that I take my subset some subset of the variables. Okay? And so maybe what I'll do is I'll try to do that in this example. Let's say that I'm going to do this for the subset A equals, let me just use the same thing that I used in the notes, 1, 4, and 5. Okay? So what I'm going to do is the following. Actually, I'm going to do almost what I was saying here. Let me optimize the basis according to this set. In other words, what I'm going to do is let's assume that connections 1, 4, and 5 cost $1 million, and the other ones are free. Maybe that's not too realistic, but I'm just going to pick a vector that has 1 in these coordinates and 0 otherwise, and I'm going to put it in here. So this is the vector 1, 0, 0, 1, 1, 0, according to this set. Okay? And I'm going to look at, this is actually not an accurate picture. This points like this. I'm going to look at what are the bases that optimize this direction. Okay? I'm going to look at the phase that maximizes this direction. This is something kind of standard to do in polytopes. So let P sub A be the phase of P which is maximum in direction A. Okay, the one that has the biggest dot product with the indicator vector of A. You put ones in the positions where A is and 0 otherwise. Okay. So let's do it here. What is or are the optimal bases of this polytope with respect to this guy? I need to maximize x1 plus x4 plus x5. So who has maximum x1 plus x4 plus x5 here? Well, let's compute it. So here x1 plus x4 plus x5 is 1. Here it's 2. 1 plus 0 plus 1. Here 1 plus 1 plus 0 is 2. 1 plus 1 plus 0 is 2. 1 plus 0 plus 1 is 2. Okay? And that's why I pointed in this direction, because actually all of these guys have the same dot product with this vector, and this one has a smaller dot product. Okay? And so it turns out that the maximal phase in this direction is actually this whole phase. Okay? Now let me tell you a fact about generalized permutahedra, which is a crucial fact. Whenever you do this, the phase that you get is always going to be of the form polytope times polytope. Q times R, where the polytope Q lives in RA, and the polytope R lives in R to the E minus A. Okay. So what am I saying here? I'm saying that this square is actually the product of two polytopes. How is the square a product of two things? Well, it's this times this. So let me get it in the right order. It's this times this. And why does the order matter? Well, because I'm saying that in the left-hand side, I'm going to restrict to the coordinates of A, and in the right-hand side, I'm going to restrict to the coordinates of E minus A. Okay. So in the coordinates of A, I'm looking at coordinates 1, 4, and 5. Okay. So in coordinates 1, 4, and 5, 1, 4, 5, maybe I'll circle them. One, 4, 5, 1, 4, 5. Okay, you can see that I have 1, 1, 0 here, 1, 0, 1 here, and here I also have 1, 1, 0, 1, 0, 1. Okay. So in coordinates 1, 4, and 5, I just have 1, 1, 0 over there, 1, 0, 1 over here. In the remaining coordinates, I have 1, 0, 0 in the top, and 0, 1, 0 in the bottom. Okay? And so this polytope is this times this in a canonical way. Okay? And actually, if you look at this from the matroid point of view, you'll see that this is precisely the matroid of the restriction, And this is precisely the matroid of the contraction. That's something you have to check. But that means, that should suggest that this is a good definition of restriction and contraction, is that I should call this guy the restriction and this guy the contraction. Okay? So we define the restriction to be Q and the contraction to be R. Restriction and contraction of A with respect to A. Okay. So that's how I restrict and contract in a generalized permutahedron. It's a polytope, right? And if I want to restrict and contract to the set 1, 5, 7, 8, 9, then I point in direction 1, 5, 7, 8, 9, and look at that face. And that face is canonically going to be a product of two polytopes. The first one I'm going to call the restriction. The second one I'm going to call the contraction. And it is a fact that those two polytopes are also generalized permutahedra, which is important because we want to be closed under the operations. Okay. And so this is going to be my geometric definition of restriction and contraction here. Yeah?
You're sometimes doing this restriction and contraction with respect to the same thing multiple times when you do your co-product.
So I haven't defined the coproduct, but it might be that, right. It might be that when you point to 1, 3, 7, 8, 9, you get something times something. And it might be that when you point to 1, 7, 8, 9, 10, you end up, even though you're pointing in a slightly different direction, you get the same face. And so it might be that you get some kind of that can happen, basically. Okay. Okay, so given that allows me to define the coproduct just like I did for matroids. And that gives me maybe the main theorem of today. And this is the theorem of that mystery paper that will exist soon. The product given by product of polytopes and the coproduct, where the coproduct of P is the sum over the subsets of E of the restriction tensor the contraction, make this into a Hopf algebra. Give rise to a Hopf algebra of generalized permutahedron. Okay. So this plan works, basically. Our plan to make this into a Hopf algebra works. And maybe I'll quickly make a table here. I'm going to save it. I'm going to put a theorem right here, but I want to kind of make a quick table here, saying the following: for generalized permutahedra, we can take restriction and we can take contraction. Okay. Now, I said that for graphs, I have the generalized permutahedron of a graph. And so you can ask, what happens if I restrict? What happens if I contract? If I take the generalized permutahedron of a graph and I restrict, you're kind of hoping, cross your fingers, that it's something nice, and it turns out to be the generalized permutahedron of the restriction. When you contract, again, you cross your fingers, you hope that it's something nice, and it turns out that what you get is, you might have a couple of guesses for what can happen. It turns out what happens is you're restricting to v minus a. So restriction and contraction interact nicely with the family of graphs. If we do this for matroids, I kind of anticipated this already, that if you apply restriction and contraction to a matroid, you get precisely the polytope of the restriction and the polytope of the contraction. So restriction and contraction of polytopes, again, interacts beautifully with restriction and contraction of matroids. When you do this for posets, and you apply this to the generalized permutahedron of a poset, it turns out that what you get is one of two things. You get either the generalized permutahedron restricted to or the poset restricted to A, or 0. Or, I mean, rather, you don't really get anything, because some phases are at infinity. And again, here you get restriction to P minus A, or the empty set. And this is depending on whether A is an order ideal or not. Okay, so this is if A is an order ideal, and this is if it isn't. Okay. So the point of what I'm writing here is that these operations generalize the operations of the Hopf algebra of graphs, matroids, and posets. Okay? And so a restatement of this theorem is that the Hopf algebras of graphs, matroids, and posets are subalgebras, or sub-Hopf algebras of the one of polytopes, of the Hopf algebra of generalized permutahedron. Okay. So it's the statement that I was saying, that these different Hopf algebras that we are familiar with, they all live inside this bigger one. Okay. And that'll be good news if we can prove some nice theorems about this one, because what we can prove here has the potential of descending to all of these three. So let me tell you then. I think maybe the hardest homework problem that I've given you is well, it's a tough contest for which one it is. But one of the ones that was the hardest was asking you for the antipode of this Hopf algebra of graphs. Right? That's, that is a hard problem, and it's this one, right? Okay. I did give you a formula for the antipode of posets, and this was a formula of Schmidt. And I haven't given you a formula for the antipode of matroids because there wasn't really one. Okay. But it turns out that there was one, but not optimal. But it turns out that actually the formula for the antipode here is just absolutely beautiful. I mean, I like it. I shouldn't say things that we discovered are beautiful, but I think they're beautiful. So I don't know. Hopefully you'll agree. the theorem is the following. This is also in this future paper, that the antipode of the Hopf algebra of generalized Permutahedra is the following. The antipode of a polytope is sum over the faces of the polytope of minus 1 to the dimension of p minus the dimension of q times q. Okay? That's it. And one thing you'll notice is that this formula is optimal. There can't be any cancellation because there's precisely one term per face, and all the faces are different. And so you know that very often in these formulas, a lot of terms are equal to each other, but here there's absolutely no cancellation. For example, what is the antipode of this guy? Well, you know, it's that guy minus the faces plus the edges minus the vertices. Okay? So it's very simple. And as corollaries, we get that if we know the antipode for generalized Permutahedra, and this formula is kind of the optimal formula, then we're going to get the formulas for all of these guys. Okay? And so if you look at what happens for graphs, we get the Humpert-Martin formula for the antipode of a graph. Okay, so that was that very hard Homer problem. Remember, it had to do with some acyclic orientations and things like this, but I think this gives a very nice explanation of what the formula actually is, and then it's easy to deduce from this their form of the formula. Okay, you can also deduce from this the Schmidt's formula for the antipode of a poset, and this is something that we did a few weeks ago. But in particular, one thing that you get, which as far as I know is new, we get a new formula for the antipode of a matroid. Okay? And I guess the thing that I would say about that is that it didn't seem like this. I mean, there are some formulas for this, but not the optimal somehow. And I guess the thing is that I think this point of view illustrates that the polytopes are kind of in my view, they're the right way of understanding these formulas. This is an absolutely cancellation-free formula. And so if you want to know the antipode of a matroid, really it's given by the matroid polytope. You just take the matroid polytope and then just go to all the faces of the matroid polytope. Now, the thing is that, so some people that do matroid theory are very happy with the polytope, and I'm one of them. I like the matroid polytope, and so I like this answer a lot. But if you don't often think about the matroid polytope point of view, then it's actually not easy to say combinatorially what that means. In the polytope, it's easy to say go to all the faces of the polytope. But combinatorially, it gets kind of ugly when you write that down, what that means combinatorially. But yeah, so this theorem kind of summarizes what the antipode is for all of these guys. Okay. Let me just conclude very quickly by saying that actually the way we prove this formula is closely related to what Brian was suggesting. That when you try to do this computation, it's the usual thing. We actually start with Takeuchi's formula, and Takeuchi's formula has a lot of cancellation, okay? Because the same term appears many different times, sometimes with a plus sign, sometimes with a minus sign. And we kind of control those cancellations precisely through a computation of an Euler characteristic. This is one way of taking ones minus ones, ones minus ones, and showing that they add to 0 is by saying, well, that's just the Euler characteristic of a sphere, and so I know that that sum of 1s and minus 1s is just this. So the proof actually comes down to an Euler characteristic computation. So yeah, that's kind of the story that I wanted to tell you about this stuff, and I think next class we'll switch gears and talk about something pretty different. But, so let's stop there.